In this video, we're going to be looking at how to find the shortest distance between a line and a point. So recall that we can write down the vector equation of a line as a position vector, in this case 4i minus j plus k, plus lambda times the direction vector, in this case I plus 2j plus k. So we've got this line which is embedded in 3D space, and we want to find the shortest distance between that line and the point 3, 2, 8. Now we can actually use our vector product in a very clever way to find this. We can do this using the dot product, but this is a real shortcut. So here's the picture. We imagine we've got our line here, and then let's say here's our point. So what are we looking for? Well, we're looking for this distance here, where we've got a perpendicular there. That's going to be the shortest distance between the point and the line. So this point here has coordinates 3, 2, 8. Now, the equation of this line specifies a position vector which is somewhere on the line. So let's say that's here. It doesn't really matter, but just for the purpose of our picture, let's say that's here. So that's the point 4, minus 1, 1. Okay, so here's our strategy. The distance here is part of a right angle triangle. In fact, if we were to find this length here, and if we could know this angle here, then the answer would be this length times sine of theta. Now, length times sine theta, that is slightly reminiscent of the vector product, and that is indeed where we're going with this. So firstly, let's find just what the vector is from this point to this point, and let's call it v. So in this case, v, and I'm going to switch to columns here. Let's just do this point minus this point. The direction actually doesn't really matter here. So 3 minus 4 is minus 1, 2 minus minus 1 is 3, and 8 minus 1 is 7. So the answer is going to be mod v times sine theta. So that's what we're looking here. Mod v times sine theta. Okay, this is pretty close to being the vector product, but the vector product between what and what? Well, nothing really so far, but here's the really clever insight. What we're going to do is we're going to find a unit vector that runs along the line. So I'm going to call that u, and that little unit vector should have a length of 1, but it should be running along this direction. So how do we find that? Well, we find that by taking this direction vector here and then scaling it down by its own modulus so that we find a unit vector, a vector of length 1 running in that direction. So that's effectively going to be the vector I plus 2j plus k divided by the modulus of I plus 2j plus k. So what is that? Well, the modulus down here is the square root of 1 squared plus 2 squared plus 1 squared, which is root 6. So what we've got here is 1 over root 6 multiplied by the vector 1, 2, 1. So that is our u. That's a unit vector running in the same direction as the line. And here's the really sneaky bit. What I can do is I can say, give me the modulus of u times the modulus of v times sine theta, because theta is indeed the angle between v and our little unit vector, and the modulus of u is just 1. And look, this is almost exactly the vector product. In fact, the only thing missing between this and the vector product of u and v is our little n hat, but we can get rid of that by simply taking the modulus of the vector product of uv. So this is just the modulus of the vector product u times v. As a little reminder, if I was to work out the vector product of u and v, that would be the modulus of u times the modulus of v times sine of the angle between them multiplied by n hat, where n is a unit vector perpendicular to both. We don't care about that vector, but taking the modulus gets rid of that, and we're left simply with the very thing we were looking for, which is 1, that's the length of our vector u by design, times the length of the vector v times sine theta. So I've basically got everything I need now because I have u here and I have v here. So I can just find the vector product of those. So how do we do that? Well, u crossed with v is going to be, I'm just going to pull that 1 over root 6 out. And then we're going to find the determinant of this matrix. So I, j, k. Then we've got u, 1, 2, 1, and v, minus 1, 3, 7. Because we're finding the modulus, the order doesn't matter. You could do v crossed u and it'd be the same. So what do we get here? We get 1 over root 6, and then it's I times 14 minus 3, so that's 11. J times, it's going to be minus j times 7 minus minus 1, so that's 8, but so minus 8 is always negative for the j component. Then k times 3 minus minus 2, so 3 plus 2 is 5. So that's u crossed with v. All I need to do is find the modulus of that. So the modulus of u crossed with v, I can just keep that 1 over root 6 out here, and then it's just the modulus of this. So 11 squared plus 8 squared plus 5 squared. So evaluating that, we get root 210, or rather 1 over root 6 times root 210. Those two, we can just divide 210 by 6, and we get root 35. So root 35 is the shortest distance between this point and this line. So we can generalize that basically by saying, oh, we've basically got it generalized, right? It's just the modulus of u cross v, where u is a unit vector that runs parallel to the direction of our line, and v is the vector between any point on your line and the point you're looking for. And the reason why it doesn't actually matter where that point is on your line is it's kind of taken care for by the fact that if you move this point, the theta there changes. So any position vector on your line will be fine. Okay, let's try another one. So same idea here. Why don't you pause the video and try this one for yourself? I do find that a picture really helps, by the way, just to remind myself so that I don't make any silly errors here. So here's the point 3, 2, minus 1. We're looking for the shortest distance here. Here's the point on our line. Our position vector here is 3i minus 4k. So that's 3, 0, minus 4. So there's our v. And our u is a unit vector running along there. So let's find those. So v is just the position of this minus the position of this. So 3 minus 3 is 0. 2 minus 0 is 2. Minus 1 minus minus 4 is 3. So there's v. Our u is a unit vector that's parallel to our direction vector here. So in this case, that is 1 divided by the modulus of this, which is root 1 plus 2 squared plus 1, which is root 6, same as the previous question. It won't always be root 6. And then minus 1, 2, minus 1. So the shortest distance between that point and the line is the modulus of u crossed with v. So let's find u crossed with v. U crossed with v, I'm going to pull out that 1 over root 6 just as I did in the previous question, and it's the determinant of this matrix. ijk, u minus 1, 2, minus 1, and 0, 2, 3. Not forgetting the 1 over root 6. What do I have? I times 6 minus minus 2 is 6 plus 2, which is 8. The j component, which will make negative at the end, is minus 3 and 0, so that's minus 3, so it's 3. Then k, and it's minus 2 minus 0, so that's minus 2. So there's u crossed v. All I need to do is find the modulus of that. So that's going to be 1 over root 6 multiplied by the modulus of that, so 8 squared plus 3 squared plus 2 squared. And this ends up being root 77, so our final answer can be root 77 over root 6. Of course, there's Going to be other ways of writing that, like the square root of 77 over 6, or peering at my calculator, root 462 all over 6. So that is how we find shortest distances between lines and points using this clever vector product technique. Okay, that's all for now. See you in the next video.